Hi, this is Bob Westervelt, and I'm happy to introduce Evelyn Hu, who will give tonight's seminar. Evelyn.
Thank you, Bob, and thank you everyone for being here tonight. So I'm going to tell you about one of my life's loves right now, quantum defects. And right here is an example of a quantum defect. It is a material I'll talk about later. It's called silicon carbide. And it's defective because it doesn't have every atom in its right spot. And right here is an image of a neighborhood of quantum defects. And each of these symbols, the triangle, the blue and purple spots, represents a different defect. They're together in a certain kind of neighborhood that I'll talk about later. And the question is, when I say, what do they talk about? How they exchange information, and how they exchange information is critically important because we need to understand how they exchange information in ways that we understand so we can make the best use of the information that quantum defects can provide. So let me just quickly show you this panorama of pictures. This is a story that actually began a few years ago with students and postdocs who have now moved on. Some of the theory was done with Tim Caceres in physics and with one of his students, Roderick Quate Defoe, who just went to Princeton as a postdoc. So I just wanted to let you know that what I'm going to talk to you about today is in a way simple, in a way just the beginning, but it takes a village to even do the very simple to understand even what we call defects. So I'm going to actually use terms that you may not understand or may not be clear. So please ask me, question me about it, because I sort of don't have the full time to set up the background, maybe in a way that would be more unifying for all of us. But I think you may have heard the term qubits or quantum mechanical bits. In analogy to bits that we use, digital bits, zeros and ones, they're the basic unit of information, but they're the basic unit of information in a way where we can use their quantum mechanical properties to interact, to entangle, to superimpose, and I'm throwing out all those terms loosely. But I'm going to say, out of the entire universe of qubits, I'm going to tell you a story about one possibility of qubits that we've been working on. I'm not going to give you the broad brush, but I'm going to say, in posing this question, I'm going to suggest some of the desirables about qubits that we might want if we're looking for a system. So spin is a quantum mechanical property, and the ability to do quantum mechanical operations means that we would like to preserve the direction of a spin or its coherence for times long enough that we can make two qubits or two spins interact. So what if we could create qubits that have long spin coherence times, and where those spin states could be initialized and read out by photons? And that makes it easy because we know how to work with lasers, and we know how to sort of non-invasively, hopefully, shine lasers on systems and prepare those states with a particular starting state. And where we could create the qubits within their own protective isolating environment so that we mitigate decoherence and we try and preserve the quantumness of our qubits for as long as possible. And suppose we had all those qubits, all these properties, and we could do it at room temperature. And for those of us who work with these kinds of concerns for qubits or even for regular devices, not having, although there are beautiful, beautiful experiments and beautiful qubits that are whose lives take place at liquid helium temperatures or much lower, there are certain pragmatic advantages in being able to do operations at room temperature. So I'm going to answer my question and say that for us in my group, the what ifs are answered by a material called 4H silicon carbide. 4H is one of about 200 polytypes or different crystalline structures in silicon carbide, all involving silicon and carbon in some periodic regular structure. But these are quantum mechanical defects, and the defects you see here, these are silicon vacancies that I'm going to be talking about. They may look, a vacancy is a vacancy, a missing silicon atom is a missing silicon atom, but they're actually at two inequivalent sites. There's one called a hexagonal-like site and one a cubic-like site. It's a material that you may never have heard of silicon carbide before. You've probably all heard about silicon, but silicon carbide is what's called a high bandgap material that people have been exploring for a long time, and that's already in manufacture for high frequency, high power electronic devices, as well as for optical devices. So it's a material that we can get a hold of fairly easily. There are 4-inch wafers and there are 6-inch wafers of silicon carbide that you can get commercially. So this is the main actor in the story I'm going to tell you today. And this is these defects, these silicon atoms, these vacancies where there should be silicon atoms are the main players. And the question is, I've called it a defect. That's sort of a leading term. It implies certain negative, that has a certain negative connotation. Is it really a defect, or in fact, is it an asset? If it's going to operate as a qubit, it can't all be just defect. So I suggest that we maybe think about the system in a half full rather than half empty way. And rather than focus on what's missing, take a look here where the defects are. Think of atom-like entities. After all, where there are these missing silicon atoms, there are still electrons that surround that area. There are still electronic states and possibly spin states. So think of those atomic scale entities as sort of units with their own electronic and spin states, and they're embedded in this matrix of a silicon carbide wide bandgap material that electrically isolates the silicon vacancies. And I'll show you another example of this, what I mean, in just a minute. So if we think of it this way, what are the electronic, photonic, and spin properties of this defect that lend it such great credence as a possible qubit? So let me show you another aspect of how we represent a defect. And this is from the sort of semiconductor device community, where it's a very simple diagram that shows a valence band, a conduction band edge, and here's the conduction band, separated by a region where there, in the perfect crystal, there are no allowed energy states. That's called the band gap. In the case of 4H silicon carbide, that band gap has an energy of about 3.3 electron volts. The way we represent a defect in a semiconductor is to say that when we disrupt the material, we create an energy state that formerly was not present in the band gap. And so we represent, for example, the silicon vacancy, and this is a negatively charged vacancy that becomes important. We represent it by an energy level within the band gap. So this is a negatively charged defect. I actually have an electron occupying this defect level. This figure 1.24 to 1.3 electron volts above the valence band is from both theory and a little bit of experiment that suggests this is the approximate energy level. So this is what it looks like. If you're a semiconductor device person, It is an energy state within the band gap. And because if it's sort of mid gap, and this is 3.26 electron volts, it means that this energy state is very far away from electrons in the conduction band or electrons in the valence band that could interact and mix or mess up the defect. And when I say very far away, if I tell you, and you may know that KT at room temperature is 26 millielectron volts, and this band gap is 3.3 electron volts, it says likely by thermal processes alone, this defect is not going to be compromised by the surrounding electrons of the semiconductor. But let me look at it in another way and talk about the energy diagrams of the ground state and the excited state of this silicon vacancy. It turns out that the excess spins for the silicon vacancy has a net electron spin of 3/2. So there are the projections of the spin states, plus or minus 3/2, plus or minus 1/2. Ground state, excited state has both electronic, and part of those electronic states are the spin states. And so what's interesting here is that you see the ground state and excited states, the spin states that contribute to it, the spin preserving transitions are about equal in terms of the energy level, that is the photon that it relates to the excitation and de-excitation of these energy levels. But here's an interesting thing that characterizes this defect and the kinds of defects we use as qubits. There is something called, this MS stands for metastable state or a shelving state. And what this does is, as I pump up electrons from ground state to excited state, this metastable state skews the spin state of the electrons or the photon transitions that I see in the following way. This metastable state has a higher transition rate from the excited plus or minus 1/2 compared to the plus or minus 3/2. So what I see is, and this metastable or shelving state sort of takes those electrons that I pump up to the plus or minus 1/2 state, they take them out of circulation. And they hold those electrons, and then with the final return to ground state, it's a dark transition. So what happens is I begin to pump the system over and over again. There's a natural filtering out so that I eventually see, when I see that photon state that corresponds to the silicon vacancy, I can begin to associate it with the 3/2 state. So this, what happens is that I have, nature has given me spin states that by virtue of the shelving states are coupled with the photon state I see, so that it enables me to do that what if that I asked for, optical preparation and readout of spin states. And then this, if I want to sort of rearrange everything, I can just sort of mix the spin states by applying a microwave signal that is about 70 megahertz. But that's a level of detail where I'm not going to get into today, because we'll focus on the optical properties. So basically, the important thing is there's an intimate coupling of spin and photons that allows us to prepare and read out spin states using photons. And that photon, which is characteristic of the transition between excited and ground state, is a signature. Since it's related to the spin state stays localized within the semiconductor, within the crystal. The photon is a flying qubit that can be propagated over long distances and read out. So we can get as if a messenger that tells us the situation of what's happened back here in the material. So I have to just take a brief moment to talk about very, very briefly. Nature usually gives you materials that are not perfect. Nature can give you material with those defects. But when we're trying to deliberately make qubit systems, we would like to have a degree of control. So we make vacancies, and we make vacancies by insulting the material. So we apply a disruptive energy source to the silicon carbide. There are lots of different ways. So these blue flying projectiles are the disruptive source, whether they're ions or electrons. And this is the perfect single crystal in yellow. And the goal of this disruptive source is to break bonds and form vacancies. Now, given this very simple cartoon-like explanation of what we do to make the defects, you can guess that the challenge is, how do we make the defect that we want? How do we get a single silicon vacancy rather than get a carbon vacancy, or a silicon and carbon vacancy that are correlated, or just silicon and carbon that are interstitial, or silicon and carbon on the wrong sites? Because you don't get to insult the material and just say, please make me one defect right where I want it, and exactly the kind of defect I want. And to compound that, those different charge states, I told you I wanted a negatively charged silicon vacancy. I want a negatively charged silicon vacancy because depending on whether the state is negative, neutral, or positive, I may or may not get light emitted from the transition. So it makes a difference. And this diagram down here is just to tell you that as I change EF over EG means something about the doping of the semiconductor. EF is the Fermi energy compared to the band gap. It just says that depending on what the material begins like, that there is a whole host of different defects. They have different energies of formation. So some are more likely to form than others, depending on the nature of the beginning material that you begin with. So at the end of this, you should come away with the feeling that this doesn't seem like a controlled system at all. And what can I hope to see out of this system? Well, to give you an idea of what we can hope to see, and to bring up another challenge, we're trying to create atomic size defects, vacancies. How can we get that strong photon signature and the spin signal from these atomic scale defects that are buried deep in the silicon carbide? And to prove my point about how hopeless this seems, I just want to show you a photoluminescence spectrum that we take. At room temperature, I told you that this was supposed to be a great system to use at room temperature. Here's room temperature, almost featureless. This is a nothing spectrum. Where's the information here? Then I cool this down to liquid nitrogen, and I begin to see a little bit structure. The V1 and V2 correspond to those two different silicon vacancies that are inequivalent. But if I show you the PL even at liquid nitrogen temperature, it looks pretty hopeless, because how are we going to find the signature? Moreover, so it doesn't look very promising from the point of view of getting a distinctive photon signature out of this material. And then to compound it, to go back to my original question, I'm creating tons of defects. In the region that I've created the defect I want, whether it's V1 or V2, the silicon vacancies, who knows what other defects I have and how those defects might interact with V1 and V2. So what am I going to do? And I'm going to show you the common solution, and I'm going to rush a little bit through this because I'm realizing that I need to sort of go through this a little bit more quickly. the common solution I'm going to show you is created by Gruntwork, which is the creation of a special nanoscale test bed that will serve to illuminate what is going on locally with a defect. And that is called that nanoscale environment. Some of you perhaps have heard this term already. It's called a cavity. What's a cavity? There are fancy definitions. Maybe some of you know those fancy definitions. Let me just say it's, for our purposes, it's an optically isolated environment that has discrete photon states. And it is an environment that is designed so that it will couple with this coupling constant G. Those photon states will couple or interact or be resonant with the electronic states of the emitter, which is our vacancy. It is a system, the cavity, that has very low optical loss. And basically what that means is we have to ensure that the electronic states of our defect get enough of a chance to go over and over to interact with the photon states of the cavity. So we need to ensure that we don't lose photons to enhance the possibility of interaction between photons and the defect. And it's a way that we design to produce a precise and distinctive amplification of the emitter signal. And to cut to the chase, once I showed you this spectrum previously, you're gonna hopefully believe me. I'm gonna show you what this bespoke cavity looks like in the next slide, but at room temperature, this is 77 Kelvin. This is once I have a silicon vacancy in a cavity, untuned, and you'll see what I mean by tuning, at room temperature. Look at the change in the signal to noise. This is a transition that corresponds to V2, which looked like this in my earlier PL. I monitor the goodness of the cavity by looking at lambda over delta lambda, which is on the order of a few thousand, and that's called the quality factor. I want to say this is not just a filter. It's not just like I put a filter around V2 and just took out the other parts of the spectrum. This slide has a lot of information. I'm going to unfortunately dump a lot of information on you in a very short amount of time without explaining. So if you have any other questions, please contact me. I just want to tell you that this is an active conversation between, and a unique conversation between, the electronic and photonic states of the defect within the cavity. So we look at a Purcell factor, which is the ratio of the emission rate of the photons from our defect in free space here compared to the emission rate in the cavity. Our hope is to increase this by a factor of 1, 10, 100 more. And how do we increase that? Well, partially, we make a finely tuned resonator with a field that's confined to a very small volume, number one. And number two, we place, if we can, the defect or the emitter right at the sweet spot, the maximum of that electromagnetic field. So I'm going to show you what this means in the next slide. But again, it's not just a filter. It is an active conversation that actually changes the spontaneous emission rate of the cavity, of the defect. So this is what our cavity looks like. This is silicon carbide. It looks pretty humble. It's a sort of narrow bridge that's suspended over the substrate. It's a series of holes in silicon carbide. It's a suspended one-dimensional structure where the holes means there's a modulation, a periodic modulation of index of refraction. That leads to standing wave patterns of specific frequencies of the right frequency of light. That's represented by these simulations, top down and side view, which says that This cavity is designed to create a standing wave pattern where we get areas of really high electromagnetic field exactly at the resonant frequency of our emitter and confined to very small volumes, roughly 100 nanometers cubed. And this is the side view. So imagine putting the silicon vacancies or emitters right there at the sweet spot. So this is a finely tunable instrument with a pure response. What do we get when we use these cavities and we actually tune? And these are done at low temperature because we wanted to elicit the full response of what the cavity was doing for the vacancy. Here's actually V1 prime and V1. So I didn't tell you that V1, which is one of the vacancies, actually has an excited state V1 prime and as well as a V1. So here's the cavity mode, V1 prime, V1 before we tune. What we do to tune is we actually change the resonance state of the cavity by actually absorbing gas. So we tune, you know, it just as you have a wind instrument and you can tune that wind instrument by the thickness of the wood or changing the geometry. That's what we're doing. We're changing the geometry reversibly. And so can be seen with each tuning step, the resonant wavelength. Here's the cavity mode. It first redshifts so that it becomes resonant with V1 prime, and it enhances the signal by a factor of 75. Then it moves on, becomes resonant with V1, and it enhances the resonance by a factor of 22. So we're getting on. I've told you the beginning of the story, and I only have a few minutes left, and it looks like, on the one hand, we've sort of done a good job in trying to bring out the signature of the vacancy, but we can do much better. And I haven't begun to tell you about how defects speak to each other and what do they say. So basically, this slide says, okay, what can we do that is better? And there's so many things that we can do better, but the next and last few slides I want to say is, can we learn more about and control the defect environment and placement? So I showed you the amazing thing. We tuned into resonance with a signature. What more can we learn? And what more we can learn is to say, this is the cavity that I talked about before. I talked about tuning into resonance with one silicon vacancy, which is this blue. And that silicon vacancy, I really didn't know exactly where it was. I knew that it probably wasn't at the sweet spot of the cavity because there were different things I would expect. But in point of fact, this is what the neighborhood might look like. A whole bunch of defects hanging out in the same area where I want to pick out a unique signature from a silicon vacancy. So what can I do? How can we learn more about this neighborhood? So the fact is that this cavity already gives us a great way of being able to interrogate what happens in the neighborhood. And the experiment we did is, okay, let's rattle up the neighborhood a little bit. The experiment that was done by Mina Gadala, one of students who recently graded, was he said, okay, let me try to see what happens if I irradiate this cavity with lasers at 3 different wavelengths, 785, 532. This is sort of red, green, and then above the band gap, 325 nanometers. Irradiate them for different powers, at different powers, and for different times. And Mina tried tens of minutes to several hours. So here's the premise. I'm just going to try and see what happens when I try different laser wavelengths, that's different energies in the photons for different amounts of times. And I'm going to use the small cavity volume and the photon amplification it gives as to create a kind of nanoscope to tell me what's going on. So here's what Mina saw. Here's the data when he illuminated it in the red, 785 nanometers, 50 milliwatts. So these are spectra for different illumination times. The start, after 1 hour, after 2 hours, after 8 hours. Now, I don't know how many experiments you've done, but there are a few pretty amazing things about the spectrum. Number one, that illuminating over 8 hours, we still saw a strong signature, and there was a steady increase in the peak intensities of the vacancy. This is not a heating effect, by the way. We did the experiments. And the average increase in the intensity of the output was about 20%. And this is a different way of showing what happened. The percentage change in the photon output, 2 different beams, 2 different cavities as a function of time. So that's good. We made the light output increase. We don't quite know why or how we did it. But here, I'm going to show you something, and I'm going to say that it's pretty amazing. We then did exactly the same experiment using a green laser, 532 nanometers, slightly lower power, 30 milliwatts. We saw, in some sense, the same behavior, an increase in the photon intensity. But we saw that it took only 20 minutes instead of 2 hours to reach that same limiting value. So a couple of things. The intensity of the photon intensity increases, that's all good. After even long illumination times, it doesn't change, it keeps high, that's good. But what is the difference between red illumination, green illumination to have this orders of magnitude change in what happened? So ordinarily, I would like us all to figure out what's going on, but in the interest of time, which I'm very short of, I'm going to cut to the chase. And I'm going to leave you with a lot of questions, but I welcome those questions after today. So here's the deal. Let's go back to that diagram I told you that semiconductor device physicists look at, which is here's the silicon vacancy, and it's negatively charged. So if it weren't negatively charged, here's the energy level of a neutral silicon vacancy. The important thing is the negatively charged silicon vacancy is the one that gives off photons that we can count. The neutral charge silicon vacancy actually gives off a dark transition. So these, you can imagine that these are 2 defect states, and that to begin with, there is some statistical population of neutral and negative. And so that the purpose, and watch the electron in the valence band, we add lasers, the red and the green, and see the energy of the red and the green compared to the energy level of the silicon vacancy relative to the valence band edge. Both of them have enough energy to induce an electron from the valence band to populate a silicon vacancy, therefore creating more negative silicon vacancies. Okay, so that's it. That's the reason that we get more optical output, because we're making more of these silicon vacancies negative. But if that's the reason, then look at red and green. They both have enough to make this transition. So why is there such a much bigger effect of the green than the red? And this is where we bring the neighborhood in. And this is our postulation, that it's not just silicon vacancy existing by itself. it exists in a neighborhood where, so these are plotting energy states, but think of these energy states. They're close in energy states, but they're close physically, close spatially. And the point is that red is enough to induce the charge state change in the silicon vacancy, but it doesn't quite have enough energy to make the transitions to the carbon vacancy or the silicon carbon divacancy. So, I'm using a lot of jargon. The point is the red is good enough to make this transition, but the green has more energy. It has more capability of changing the charge states of the other defects in the neighborhood. And once you change the charge states of these other defects and maybe promote the electrons to conduction band within the neighborhood, the benefit of the green is that the green allows us to go up the step ladder of energy levels, defect levels in the silicon carbide, and makes that transition or that charge state change go much more rapidly. Anyway, that was it, very quickly, the main point I wanted to make to you, and also to tell you we're just at the beginning of everything that we're going to explore. We also want to know what I've talked about is charge state change to increase the photon emission. But is it possible actually to actually move? So I show you a silicon vacancy. Is it possible for me to direct energy to that silicon vacancy so I can nudge it into position? And I'm just showing you some preliminary data, both thermal annealing and actually the UV irradiation that suggests that we can. I've taken enough of your time, and I've probably dumped a whole bunch of information all of a sudden on you. I just want to take this time to conclude. This is just, I hope, an introduction to talk about silicon vacancies and the power of optical nanocavities. The very exciting potential that once we have the defects within the cavities, we can use those cavities to understand what's going on locally with those defects, what's going on in the neighborhood, the interplay between the defects. So what are they talking about and what are they saying? And understanding how and what defects talk to each other is a way that we can better control the environment and pave the way for going to more complex, scalable quantum systems. So thank you.
Well, thanks very much. It's exciting stuff and moving along quite a bit recently. Do you have questions?
And I'm going to put my email.
Oh, in the chat.
Yeah. So
Okay.
please reach out anytime.
Yeah. What is the first gadget that you'll make? I mean, the most simple device that you think you'll...
Actually, so what we're going to try and make, so two things, Bob. One of them, it's a kind of gadget. We're going to use a process. We're going to design a special structure that allow us to look simultaneously at two defects, so that everything I showed all of you before depended on a nanoscope that was focused to the silicon vacancies. And when I talked to you about how the neighbors get involved, our nanoscope wasn't very good at understanding what the neighbors were doing. So one of the things we're designing now is a nanoscope that will allow us to monitor two different defects. So this, as we see one increase, the other decrease. So that's not really a device, but it is a way that
Yeah.
we will begin to understand the conversation.
Sure, sure. Thanks. Other questions? Okay, well, thank you very much. And we'll be posting your talk up on YouTube so that people can access it.
Thank you all. Thanks, Bob, for the opportunity. Thank you all for being here tonight. And really, truly, if you have any questions at all, please reach out to me. And maybe we'll see each other in person.
Oh, I hope so. As soon as we can. All right. Thanks.
Thanks.
Thank you
Good
so
night.
much.
Thank you.
Thank you.
Bye.
Bye-bye.